Okay, this is a week 11 video. It's office hours and no one showed up, so I'm going to make this video instead. I'm going to introduce the proof material, the new Unit 2 proofs section a little bit, and then we'll do homework 11 part 2 proofs together. So in the proof, or in Unit 2, let's just take a look at what's in the proofs material. So you'll see there's a schedule here. The place to start is with video 2.1, the introduction to the proof method. So go watch that. There's no text for this section. It's lecture videos and practice exercises. And all of the practice exercises in this section have solutions. You should absolutely be doing practice exercises and not just the homeworks, the assigned homeworks. So your study plan is to watch the videos. I would watch those before you do the homework, and then decide where are you at with getting started. If you're feeling overwhelmed, pick the easiest possible thing to get started with. I recommend everybody do the drills just as a way to learn our new rules when you get into the material. You'll see we have 3 rules for doing proofs, and then these practice exercises focus on one rule at a time, and there's a little video that goes with each one. And then you can do just 2 rules at a time and then add the 3rd one and then add 2 more. Or if you watch these practice videos and you're like, I think I get it, start down here with all 5 rules at once. There are easier, medium, and harder problems in this section too. The number one thing I recommend is work at the level you're at. If you are feeling behind and you're trying to do the newer material because you're behind, it's just going to be frustrating. If you are a beginner and you're frustrated, you should do the easiest problems. Do not move on until you feel confident. And if you are feeling confident, move on as fast as you can, because there's way more homework problems to do than you probably need to do. So your task is to practice a lot and figure out what your level is and practice at that level. And I'm here if you need help. Okay, so that's what's here. Let's check out the weekly homework together. Okay, so our first question here is a big picture question, just to emphasize that this material is in Unit 2, and Unit 2 is all about proving that arguments are valid. And we've looked at a number of different methods for proving that arguments are valid, the counterexample method, the truth table method, and now we have a new one, the proof method. So this first question kind of puts together a bunch of the stuff we've learned in Unit 2. So we're given a passage. You're asked to clarify, or at least it's modeled, how to clarify it, how to translate it into symbolic notation in steps. Ultimately, here is the argument in symbolic notation. I'm telling you that it's a valid argument and saying, let's prove it. If we were to use the counterexample method, we would try to imagine a scenario in which all these premises are true and the conclusion is false. Now, hopefully, you might be able to just see that this is valid, but if it is valid, we won't be able to come up with a counterexample. And it's kind of like there's a lot of stuff to hold in your head at once. So even just trying to come up with the counterexample just feels mentally taxing and confusing, and we might worry that we missed one. So counterexample method isn't great for things that aren't super simple arguments. Truth table method. Now that we could use with this, and here is a truth table, and you're asked to complete it. So I actually already filled in this because we're not going to do this part together, but you're given the truth table and you're asked to determine whether or not this is valid. And we can see that the only row where the premises are all true, the conclusion also true. So there's no counterexample row. So indeed, there is no counterexample. I couldn't think of one. And when I did the truth table, I showed there isn't one. So this is a valid argument. Now, if we start to move beyond arguments that have just 3 atomic statements and get to ones that have like 4 or 5, your tables are going to get exponentially large. And as you start doing these, you might have thought they were fun because, it involved figuring some stuff out and But once you sort of have this skill down and the tables get large enough, you are not going to think they are fun. So the proof method, unlike the truth table method, we cannot prove that arguments are invalid with it. Once you have figured out the proof method a bit more, maybe we can think about why. Don't worry about it for now. But the truth table method, you're given any argument and your task is to figure out whether it's valid or invalid, because you can prove both with the truth table. With the proof method, you will be given an argument and it will be a valid argument. And your task is to prove that it's valid. And we're going to do that by using patterns of reasoning that we know are valid. Basically, we're going to reason in little valid steps. And we are going to start this homework with just 3 rules: the disjunction rule, disjunctive syllogism, a conditional rule, modus ponens, and I would have expected myself to have put the modus tollens rule up here, but I guess I did not. I guess we're just using syllogism, modus ponens, and conjunction. Okay, I guess that's true. So we have these 3 rules. Whenever you have a disjunction, the negation of one disjunct, you can infer the other disjunct. That's a pattern of reasoning. Modus ponens, if you know a conditional is true, you know the antecedent of that conditional is true, you can infer the consequent. That's a pattern of reasoning we know is valid. Or if you know any 2 things are true, you know the conjunction of those 2 things are true. Remember, an argument is valid when, if the premises are true, the conclusion must be true. So assume this and this is true. Then the conjunction, where we know both parts are true, would have to be true, because that's the definition of conjunction. Okay, so what a proof is going to look like then is you're given an argument. We used to be given them in this form with the conclusion at the bottom, but now when you're given arguments, they're going to look like this. We've taken the conclusion and moved it up to the side. This is a valid argument. And this is the conclusion of that argument. And you're supposed to show through a series of smaller inferences, each of which is a valid inference, that ultimately we can derive this conclusion. So whenever you complete a proof, the last line will be the conclusion that you're trying to prove. So let's do this one together. We have a disjunction on line 1. We have a rule that applies to disjunctions. That rule says if you have a disjunction and you have the negation of one or the other of either disjunct, then you can put the other one on its own line. So let's erase these. Oh, wait. That's there. So if you have a disjunction, you can put the other one on a line. And we do. We have P. We can put that on its line. We'll cite the lines that we looked at, and we'll use the rule DS. So if this is or this is true, not this, therefore this follows. So we'll put it on a line, cite lines 1 and 2, this is the rule we looked at. Now, to say that we've derived this is to say that if the premises are true, then this would have to be true. And we're assuming for the sake of argument the premises are true. So now this is a thing we can add to our assumptions. We're assuming P is true. So now we know that this conditional is true, this is true, and if those 2 things are true, then by modus ponens, if you have a conditional and you have the antecedent, include the consequent, by modus ponens, we know that B would have to be true. And we'd write that on a line, and we would cite lines 3 and 4, and we would write down the rule modus ponens. Now we've derived P and we've derived B. So if the premises are true, we know that P is true, and then we know that B is true. It follows then that P and B is true. P is true and B is true, then P and B is true. And we'll cite lines 4 and 5 and the conjunction rule. Okay, so the next bit of this question, you're just asked to complete the proof yourself, kind of like getting muscle memory. The proof is up here. You're just asked to fill it in. So, I jump to the bottom. Okay, so we know that this disjunction is true. We also know the negation of one disjunct is true. So we also know that P is true. And we know that because we looked at lines 1 and 2 and we used the DS rule. Now we know that this conditional is true. We know that the antecedent is true. So we can infer the consequent by looking at lines 3 and 4 and using the rule modus ponens. So now we know that P is true and B is true, so we can infer P and B. And we'll cite lines 4, 5, and the conjunction rule. If you know two things are true, you know the conjunction of those things is true. Now, a bit about formatting. All this formatting stuff up here matters. You'll get used to it pretty quickly, but we're not going to use any spaces. We'll always put commas between our line numbers here. We'll always put our line numbers in numerical order. Don't spell out the rules. Use these acronyms. There's only 5 rules, and I will include these formatting instructions all the time. Don't use unnecessary parentheses. That didn't come up this time, but it will in a future question. And you can either use the weird symbols, the dot and the horseshoe, or you can use these alternatives. But importantly, don't use space. So you could enter P and B the way I did here, or you could copy and paste. And if you copy and paste, you have to go remove these spaces. And I'm sorry that that's an extra step, but auto grade. All right, so that's the answer here. You've filled everything. Okay, so now we're going to sort of start from, go back a step and kind of just work on the rules here. So the next questions just ask you to identify whether or not these are examples of the rule being applied. So first and foremost, we have the modus ponens rule. That rule says if you have a conditional on a line and you have the antecedent of that conditional on another line, then you may put the consequent of that conditional on a new line. So which of these 4 examples, and there's more than one, there's 2 correct answers, fit that pattern? So number 1, we have a conditional. Do we have the antecedent of that conditional? Yes, we do. S and B is the antecedent of the conditional. So we can infer the consequent. This is an example of modus ponens. What about the next one? This is not an example. Here we have the consequent on its own line. But modus ponens says we need to have the antecedent on its own line, and then we can infer the consequent, not the other way around. If you did a truth table, this is invalid. How about this one? We have a conditional. Do you have the antecedent on its own line? Yes. Did they infer the consequent? Yes. So this is an example of modus ponens. If you were to go back up to our little rule here, notice it doesn't quite look like this schematic, but remember that Greek letters can be any statement. That's why we're using Greek letters, because usually these are plain old A, B, C, D, the familiar ones, those stand for atomic statements, but Greek letters can be any statement. So here we have a conditional, here we have a conditional and we've got the antecedent, it matches. So here phi is not Q and psi is S and B. So this is an example of modus ponens. Next, we've got this question. This is a tricky one. Here we have a conditional, we have the antecedent of that consequent, and we've inferred the consequent, but this is not an example of modus ponens because this is not on its own line. This rule applies if you have a conditional on a line. That means conditional is the main operator. This isn't a conditional. This is a disjunction that has a conditional as a disjunct. So conditional has to be the main operator like these ones above. It's not an example of modus ponens. How about modus tollens? The rule says if you have a conditional on a line, and there's a conditional somewhere on all these lines, and the negation of the consequent on a different line, then you may put the negation of the antecedent on a new line. So let's see which of these fit that pattern. Do we have a conditional? Yes. That's criterion 1. Do we have the negation of the consequent? The negation of the consequent here would be not X. Do we have that? No. So this is negating the antecedent, but modus tollens says if you have a conditional and the negation of the consequent, you can put the negation of the antecedent on a line. So this is not an example of modus tollens. Here we have a conditional, and we have the negation of the consequent, so looking good so far. And do we put the negation of the antecedent on that line? Yes. So this is an example of modus tollens.